Thank you very much. Can you guys hear me from here? Yeah, okay, great. Okay, so funny situation here, but I just want to start out by saying that Irfan Mohammed is going to graduate this summer. He's awesome. He's had many projects, and this is just one of them. So here's the outline. First of all, I'll tell you, I'm not going to advertise PCAST. I'll let that go. Why we're studying serum cobalt indium-5, apparently it's the most study of all the heavy fermions. It's an incredibly clean limit, really long mean free path and coherence length. We all know it's a dx squared minus y squared pairing symmetry. If you disagree with me, I've got the data to prove it. But we do not know what the pairing mechanism is. So just knowing what the order parameter symmetry is doesn't really tell you anything about the pairing mechanism. So we've been able to make, over the past few years, very, very reliable planar tunneling spectroscopy results. These are all on single crystals that I'm showing you. We do have thin films now. We're just starting to do tunneling into thin films, which has a lot of advantages. We've been able to get reproducible data in the three major crystallographic orientation, C-axis, A, and AB. We've covered a range of temperatures and fields up to 18T. Thank you, MagnaLab. And basically, I won't have time to go into this now, but in planar tunneling spectroscopy, if you see something that doesn't look like Ohm's law, it's non-Fermi liquid. So that it's just, I'd be happy to go over the old Harrison's theorem with you, but basically the fact that we see stuff above TC tells you, just like all the other unconventional, almost all the other unconventional superconductors, it's non-Fermi liquid above TC. And we also see background structure reproducibly about twice TC, not much higher, up to about, so TC is 2.3 degrees. We see this structure up to about 5 degrees. When we go up to T star, we don't see much, which is an important clue. We do see this interesting field-induced gap. I'll show you the data. The data will speak for themselves. And I'll just point out that the results are consistent with that F scattering, condo scattering, probably has something to do with the pairing. And I would like some help. I got Pierce's interest again. Anybody here that wants to help me out on this? I'd love to hear about it. Conclusions. I just want to throw this up on the board. This is way from 2006. This is, everything in red is conventional. We know that. We know how it works. Above TC, it's a Fermi liquid. Below TC, it's electron phonon mediated BCS superconductor. I've left, 50 different families of superconductors off this, but what unifies the unconventional superconductors isn't the order parameter symmetry. The breaking of the symmetry from the underlying lattice is the electron fluid above TC, whether it's, quantum critical, stripes, nematicity. We all know Fermi liquid, the electronic properties are determined by where the atoms are and what they are. And then you get the optical, thermodynamic, and transport properties. And but we don't do that with all these strange phases above TC, which almost every unconventional superconductor have, whether it's D wave or S plus minus or whatever. I'll also say that I don't do that much studying down in the superconducting state because everything seems to be Cooper pairs. And we know how to model that. Thank you, Bernoulli-Bogdajan equations. Now, this is our favorite. These are old data, but it's just really nice data from Petrovic and everybody. This is just to remind you that the resistivity versus temperature is non-Fermi liquid. The T star, where things got to go coherent in the condo lattice, is about T star is 45 degrees. And I also want to remind you that this is pretty heavy. M star is about 85 electron masses, and it is the heavy electrons that go into the Cooper pairing. And just to show you, it's been known for a long time. It's dx squared minus y squared. There was heat transport data that showed there were nodes. We did our point contact spectroscopy in about 2008, and we're able to show that it was where the nodes were, was dx squared minus y squared. And basically everybody agrees with that. So here's a list of papers that I actually reread again this year, which are really great papers. So the STM agree, except if you get Seamus in the corner of in one of the rooms, he'll say, well, maybe not, but pretty much everyone agrees it's dx squared minus y squared. And the STM all agree that there's something going on above TC. These range of papers, which I probably haven't listed them all, they're all worth reading. They all claim that there's something going on above TC. There's arguments that it's preformed pairs in certain directions, hybridization gaps in other directions. I'm going to argue that the answer is yes, right? It's a condo lattice. There's going to be hybridization. There's going to be phantoresonances. But inside of that quote pseudo gap or whatever hybridization area, I think we also have preformed pairs. So our measurement is planar tunneling spectroscopy. It's not STM. It's you in the single crystals, you polish it like crazy. And you've all seen these graphs. But what I want to show you is on the lower bottom right there. Here's just an example from our lab that shows you this is just aluminum with aluminum oxide as the tunnel barrier and lead as the counter electrode. And what we see here are those little bumps. Those little bumps are the 6 and 8 millielectron volt phonons from the lead. That's what was able to be proved by McMillan and Rowe, that it was, strong coupling lead phonons that caused the pairing. So one of the other take-home messages is that if you don't see the bosonic excitation in the tunneling, the electrons aren't feeling it. If they're not feeling it, they're probably not having to do with the pairing mechanism. So these are the very simple take-home messages without getting fancy. And this is just another experimentalist macho view graph that we've really learned how to make things really flat and really smooth and make reproducible tunnel junctions. And these tunnel junctions are right now aluminum oxide with a lead counter electrode. Right now, because the results are so intriguing, we're using other tunnel junctions and other counter electrodes, and that's one of the projects that Irfan Mohammed is doing right now. Now, what I want to stress is, why do we use lead as a counter electrode? We use lead as a counter electrode because we're not sure what the tunneling density of states of the serum cobalt indium-5 is. Therefore, if we go down to low temperature with zero applied field, we know exactly what lead planar tunneling density states looks like. And so that becomes a diagnostic for the quality of the junction. After you do this a bunch of times, and then you drive the lead normal. I'll show you the next one. I'll do that now. So I'll show you this right here, is that what we have here is serum cobalt indium-5, aluminum oxide, superconducting lead as the counter electrode. And here, as we expect, we see the lead phonons. We also see the serum cobalt indium-5 plus lead gap, because this is delta 1 plus delta 2. And so we know that we have really high quality junctions. Once you have a junction of this high quality, what we did in high TC is bring it up to 10 degrees, or what we can do in serum cobalt indium-5, put a couple of kilogauss on it, and serum cobalt indium-5 with several Tesla HC2 doesn't give a hoot. So you make really good tunnel junctions. You just change a little bit. So the counter electrode lead is now the normal metal. So you have serum cobalt indium-5, insulator, Fermi liquid that you're tunneling to normal metal. So here's some original data. So the top plot is the C-axis direction 001, and the one next down is the A-axis direction 100. And if we analyze all this, it's very clear. Further support is dx squared minus y squared. Looking in the nodal direction, the 110, there's certain things that are consistent, but I cannot explain why that zero bias conductance peak is so broad. So we kind of left that behind. We do things that convince us that it's the nodal direction and it's dx squared minus y squared, but I can't really fit that entire background. But if we do a BTK fit to this, we get reasonable results of dx squared minus y squared. Now, this is the temperature dependence. So what we have here, we didn't do the color plots only to get it into a high impact journal because they're actually fairly helpful for understanding this. So the top plot is the C-axis direction, and the middle plot is the 100 A-axis direction, and the bottom plot is the 110 or nodal direction. And all I want you to take away from here is, if you look at those lines, which are the I'll just point to the screen. It's better than, so that dashed white line across all three of those color plots are where TC is. And the takeaway here is that above TC, this is not a Fermi liquid. Something's going on. If you look in any of these directions above TC, something's happening. So a pseudo gap, who knows what, stripes, anything. It's just non-Fermi liquid. And we got that we know for sure, very, very reproducible. Now we're going to look at something that I found really interesting, and that's the magnetic evolution. So these data are, I'm not going to talk about the nodal direction on the right, except for the fact that in zero field, in very little applied field, it splits already, which you expect for nodal direction. So let's look at the first two. They're low temperature. The A-axis one, C-axis is 0.4 millik. The next one in the A direction is 20 millik. And we see something really interesting here. If we go to, I don't know how to point to this. Okay, I don't know how to point it on this thing. But if we go to, let's look at the left side. We have 0, 0, 1 direction. We're at low temperature and just enough magnetic field to drive the lead normal. So what we're seeing there is the tunneling density of states showing the superconducting gap of the cerium cobalt indium 5, just as we would expect. As you start raising the field, I'm sorry, some of those are blacked off, sorry. But if we go up to there, if we look, HC2 is about 5 Tesla. If we go there, the green line is 6 Tesla. So if we see going from 0.2 Tesla, where the cerium cobalt indium 5 is superconducting, all the way up to 14 Tesla, there's no superconductivity up there. What we're seeing is that we're seeing killing the superconducting gap as we expect, and then this other kind of splitting, this like V-shaped thing grows linearly with magnetic field. We see the exact same thing in the A-axis direction. So in the A-axis direction, HC2 is about 12 Tesla, and we see there at 11, 14, 18 Tesla, something's growing there, and we can't explain it. It's not superconductivity. That's the only thing we all know. We all know because we're at low temperature, but well above HC2. Wrong direction. Okay, so now the grayed out areas are the data that I just showed you. We have lots of junctions, and yes, this is really nice data, but trust me, it's reproducible. Okay, so the grayed out area are the data that I showed you. On the right side there, the white area, we have T greater than TC, but less than twice TC. So on the right side, the lead has been driven normal because this is all done in at least 0.2 Tesla. And then we raise the magnetic field, and what we see is something else that's changing as a function of field. We're above TC, but below 5 degrees Kelvin. So up to about twice the superconducting temperature, we see the same kind of thing that's growing with applied magnetic field. Now let's go to a higher temperature. Here we are at 10 and 15 degrees. And what we're doing at 10 and 15 degrees, where we're above TC, and we're applying these magnetic fields up to about 18 Tesla, and we don't see much happening. So this interesting splitting or gap or whatever that's going in that's increasing with applied magnetic field only happens when you're below TC or below about twice TC. When you go like 3 times TC, you don't see it anymore. So you've got to be close to TC. Okay, so this curve is just to show you that we do fit I don't want to take too long, so I have time to, oh, we're doing okay. So this curve here is just to show on the right side is that we're plotting both the peak to peak and the steepest slope and tunneling. There's reasons why you do both. In any case, whether you're looking at the green curve or the black curve, that splitting grows linear with applied magnetic field. And what you see in the red and the other thing is sort of the gap. And so what we do is we fit to a couple things. We fit to BTK, and we also find this linear growing with applied magnetic field. Very interesting. What does linear mean to me? Well, I've been doing this a long time, and linear says every 1, 2, 3, Zeeman splitting. Okay, but besides Zeeman splitting, that's also seen in single impurity Kondo scattering. So we're going to have a little leap of faith here. So this is very old work, but then my postdoc advisor was John Rowell, so I know all about it. Even before I was a postdoc, this is what I did with Shannon Rowell. And what they were doing is not knowing this is not superconductivity. This is looking at planar tunneling with magnetic impurities either in the barrier or very near to just somewhere in the barrier. It can be in the center or near the surface. And what they found is that you get this splitting with applied magnetic field. And this was worked out by Anderson and Applebaum. Anderson, we all know, great theoretical physicist. We're sorry we lost him. Applebaum went on to Wall Street, one of the early guys that did. So if we take a look here, let's just look at the right side. If we're looking at simple NIN tunneling. So if we have simple like copper insulator, copper tunneling, what we get on the upper right is that conductance is a function of bias or voltage, and we have Ohm's law, it's flat. Now, if we put a magnetic impurity in the center, remember tunneling an impurity in a junction opens up a channel, so it makes things easier to get through. But it's not like optical that absorb. So what we see is if we have a magnetic impurity in the center and we apply somewhere in the barrier and we apply a field, if we have, and we apply a bias, if we give enough bias to flip the spin, then we have an increase in the conductance once you give it enough bias to flip the spin. So you can have this inelastic tunneling through a spin in the barrier. Now, what I didn't go, and I'll mention here, is that you also have something called a Kondo peak, which is, I won't go into that, but it's like the third order effect. You can have an electron tunnel through, and you can have it superimpose with something that's Kondo scattering, and you can get this peak. So you have this peak there, but the important thing is that this thing grows linearly with applied magnetic field. And we fit it, and let's just talk about this. So now I'm going to make a couple jumps and make some conclusions, in which case you can all disagree, but that's fine. So this is a cartoon model that's kind of based on Rebecca Flint and Piers Coleman's model, which I'm not sure they're convinced of, but I thought it was sort of interesting. So what it is that if you have, as we all know, there's the Kramer's doublet. And I've read this paper about 30 times, probably a lot more than that. And it's very theoretical, and this is sort of a heuristic interpretation. So we have a Kramer's doublet, and what if you can have two electrons scatter off of the same F level because you have a doublet? And what if that creates some kind of coherence between the electrons? Okay, if that is the case and you apply a magnetic field, that splitting will be a Zeeman splitting and grow linear with applied field. Let me warn you, this is intrinsic to the cerium, cobalt, and 5 or any kind of Kondo lattice. The model that I just showed you was an impurity in the barrier. So there's a big jump here. I'm just saying they look like each other. And then if you get to a place where you don't have any pairing at all and you apply a magnetic field, like above 10 degrees, you're not going to see a field dependence. Okay, so there's a couple other recent studies that follow. It turns out people still love cerium, cobalt, indium 5. And so this inspired us to do a couple more experiments. Well, one in particular, shot noise. And then I will report on Tucson Parks group and my old student who's there that say something different. So the shot noise is something that is really interesting. I had a summer student that managed to put together a shot noise experiment. We haven't done it on cerium, cobalt, and indium 5 yet, but he got as far as doing it on lead and seeing a difference when you go above and below TC. But basically the idea is, the shot noise is how things clump up quantum mechanically. And so this experiment, according to Milan Allen's group and a couple other groups out there, argues that looking at the shot noise, we can tell if the transport is 1E or 2E. So this is one where they're arguing that they can see that in this disordered tin nitride, and I had the wrong element on the last slide, that they're seeing some effective charge 2E above TC in this particular disordered superconductor, which might be reasonable. Here's another example where Tucson and Xin Lu, my student who's now at Jiaxing University in Hangzhou, they said, no, Green's group is wrong. It's not wrong, it's hybridization due to, it's, the Kondo lattice shows hybridization between the F level and the conduction electron band. And I look at their data and I say, yeah, you're right. That's absolutely correct. But they also see this effect going all the way up to T star. So our argument is that we're both right, but just like and I'll put on some explanation coming up, and then I'll show a couple of plots, is that we're probably all right. There's certainly hybridization, but it looks like in this material, there is some preformed pairs above TC, and could that be the pairing mechanism in this material? So now I'm going to finish with a couple notes, and I'll finish early, yay. So we know that serum cobalt-indium-5 is dx squared minus y squared. We think that there's precursors up about twice TC. Increasing the magnetic field does as we expect. It suppresses the superconducting gap, but then a whole another thing comes up and grows linearly with applied field. It's interesting that the evolution from TC above TC to this other thing is just very smooth. You see them both at the same time. I think that's a key. If you're going above twice TC, you don't see this magnetic field effect. So there's something that you have to be near TC. So this is something, the neutron spin resonance seen in the cuprate. So when I started talking about this, everyone said, how could you say it's Kondo scattering when we know D wave means spin-spin correlation? And my argument is no. Knowing this order parameter symmetry doesn't tell you anything about the mechanism. It just tells you the order parameter symmetry. So this went on for a while, and I just want to remind you that that the spin-spin correlation is not seen there are correlations in elastic neutron scattering that's seen in serum cobalt-indium-5 in the ytterbium part, but these things are not seen in the tunneling. If they're not seen in the tunneling, the electrons don't feel them. So what's going on here? I also want to remind you that the cuprates in the iron-based superconductors don't have F levels. And I've been believing that since, I think I had to give an invited talk at a AAIS meeting 2 or 3 decades ago. And that's when I came up and said, there's not one mechanism. And people hate that because they think Occam's razor. But we already know N is greater than 2. Sorry, I've called for mechanisms. So that's an argument that there might be, there's other mechanisms. And that's what makes this field so difficult. As Dirk van der Merwe would say, you add a little paprika, a little salt, spin, there's a few phonons in there. It gets very difficult. I just want to show a couple other things here. And that is Ong's group a long time ago did the Nernst effect. And they were able to show that there was a vortex lattice just above TC. And so he was arguing, and it looked pretty reasonable, that above TC, there were preformed pairs. And then I want to point out that Doug Nadelson and group also did this looking at shot noise in copper oxide junctions. And I think these are really interesting. All you have to do is blur your eyes and see there's blue stuff above that dotted line. So something's going on there. This is not simple stuff. We're not going to get the answer today. It's just intriguing. So is this my last slide? This is my last slide. So basically, I want to point out that we've been seeing these I showed you early on, unconventional superconductors. They got all this stuff going on, and they all have pretty much, not all, it's quantum mechanics, not everything's 100%. They all have very close to the same phase diagram. And I quantify unconventional superconductors that most of them have something going on above TC that's a non-Fermi liquid. So I want to, so that's just back from 1979. Steglish and Lanzarus worked out that curve. Early on, we started to understand this. The right side is an old plot from 2005 that was recently reproduced in one of Suber-Sachs's recent paper. And it's just to show you, to remind you that the pseudogap in these regions, it's not a pseudogap. There are multiple phases that exist within the pseudogap, and it's a little complicated, and it's going to be a challenge to figure it out. And if anybody wants to help me understand this, I would appreciate it. So thank you for your time. Sorry. Excuse my cough.
We look at behavior in the sense of, does the temperature show any residual history in the T-squared to CeCoIn5?
Yeah, yeah. So just look at the resistivity versus temperature. Okay, there's nothing Fermi liquid about this, right? If you look at the very, very, very high temperature, it looks kind of like electron phonon.
Might be different.
Of course, it could be different. There's like a million phases out there. To me, all non-Fermi liquid behavior means is that the electron-electron interaction is stronger than the electron-phonon interaction. That's all it means. So at very high temperature and then at very low temperature, where you gain the Fermi liquid again. But in between, it's this great Kondo scattering and Kondo lattice. Chimia?
Or if ionization feature extends all the way to 45 Kelvin, seems like by the time temperature is low to TC, there's not full-fledged local moment anymore.
That's right.
But maybe there's some vestiges.
No, but that's the way I understand heavy fermions, is that, you have at these higher temperatures, something that looks a lot like single impurity Kondo, because there's all these electrons are scattering in the way that Miriam told us about. And then when you start going over T star, that's when you start getting coherence, and you have these local moments that the electrons now compensate for. So they're compensating for it, and and all of a sudden, most of them are compensated, and all of a sudden they say, we're below 45 degrees, and where'd all the phonons go? And the resistivity dives down. So yeah, that's exactly the way I look at it.
Evidence for this gap?
Yeah. So if you look, I'm happy to share these slides. So there's, it goes way back. Some of these say in certain directions, they see preformed pairs, they see pseudo gaps. But one of the reasons why we thought about preformed pairs when we saw this was because of the STM work out there. So,
Looks like it's straight flat and then shoots up, right?
I'm sorry.
From heat capacity. I mean, I thought, heat capacity throughput and stuff also shows sort of
Yeah.
preformed pair formation, but there's no evidence for that.
If you talk to certain people, they would argue that there actually is. This is not completely explained from what I understand, but I can't, it's over my head. You and Chimiao can explain it to me. I'm barely hanging on here, so.
Since Pen-Cheng asked 2 questions, maybe I can answer.
I'll be around until I have to go to North Carolina on Wednesday.
In the sense that in cerium copper to silicon too, there's extensive inelastic neutron scattering data, which sheds some light about anti-ferromagnetic correlations.
Yeah.
How come in 115 there's not enough inelastic?
No, there is. So there is an elastic neutron scattering in the ytterbium stuff. Yeah, this is my scientific statement, ytterbium stuff.
Oh, it's very hot. The signal goes away. No, it's very hard in Florida computing.
Thank you.
Okay, that's
Okay, thanks a lot.